What if the moment that passed a second ago did not vanish, but remained somewhere within the geometry of spacetime? Relativity tells us there is no single universal now, and the light reaching our eyes is always arriving from an earlier state of the world. The sun appears as it was about 8 minutes ago, distant galaxies as they were millions of years ago, and every memory is a physical record written into the present. But does any of this mean the past still exists, or only that its traces survive? Where are you watching or listening from? And what time is it there? Leave a comment and join the quiet community gathering around this question. Thank you for spending part of your day, or perhaps your night, with calm space science. A like, subscription, or share helps this channel continue creating calm, thoughtful journeys through the deepest ideas in physics. Now the clocks can fall silent for a while, as we follow time beyond memory and into the structure of reality itself. A room holds its history quietly. Dust settles along a shelf. Wood carries the pale marks of years, and a photograph preserves the arrangement of faces that no longer stand together. Nothing in the room announces that time has passed. Yet every surface contains evidence that it has. The present appears complete because it is the only moment directly available to experience. But it is never cleanly separated from what came before. It is built from remains, memory, scars, worn stone, starlight, fossils, ruins, and living cells all carry traces of earlier states. Even so, the events themselves seem absent. The footsteps are no longer falling. The voices are no longer moving through the air. The exact pattern of light, heat, motion, and attention that once filled an instant cannot be summoned back merely because some record survives. This difference between an event and its trace creates one of the deepest confusions about time. The past feels real enough to shape everything, yet unreal enough to be gone. Human awareness does not move freely across time. A sound, a memory, a photograph, and a fossil all enter awareness now. In every case, the evidence enters consciousness as part of the present. The past itself is never encountered directly. This makes disappearance seem natural. A moment arrive, becomes briefly available, and then appears to fall away behind the moving edge of experience. Language reinforces the impression. Events are described as finished, lost, over, or no longer here, as though existence itself changes category from one moment to the next. That picture feels obvious because it matches the structure of memory. Memory records only one temporal direction. It contains fragments of earlier events, never genuine recollections of later ones. A person can remember entering a building before leaving it, but not leaving it before entering. A tree contains growth rings from previous seasons, not from seasons still to come. A detector registers a signal after the signal has arrived, not before. The world is filled with records pointing backward. This asymmetry creates a strong sense that the past is settled and the future is open, while the present stands between them as the only point of actual existence. Yet, direct experience may be a poor guide to the structure of reality. Human senses evolved to track changes at ordinary speeds and distances, under conditions where clocks agree closely enough for disagreement to go unnoticed. At that scale, the present seems universal. Delays in light and differences in motion are too small to disturb the impression that all nearby things occupy the same now. The mind therefore treats the present not as a local condition, but as a feature of the whole world. What is happening here appears to belong to the same cosmic moment as what is happening elsewhere. The difficulty begins when that intuition is pushed beyond the scale that formed it. Light does not travel instantly. Every act of seeing is already delayed. The moon appears as it was a little more than a second ago. The sun appears as it was roughly 8 minutes ago. Distant stars appear years, centuries, or millennia in the past. And remote galaxies are seen in forms they held millions or billions of years before the present on Earth. The night sky is not a single moment spread across space. It is a layered record assembled from different depths of time. Even a nearby face is seen as it was a tiny fraction of a second earlier. Immediate perception is never perfectly immediate. Old light, however, is a message, not a doorway. It carries information from an earlier event because the physical influence of that event has continued to travel. A star may have changed or died while its older light is still crossing space. The image survives in transit, but the event that produced it is not thereby restored. A footprint can remain after the foot has lifted. A memory can endure after the conversation is over. Persistence of consequence does not automatically establish persistence of cause. Still, the opposite conclusion is not automatic either. The fact that an event cannot be revisited does not prove that it has ceased to exist in every possible sense. Inaccessibility and non-existence are different claims. A distant region beyond the observable universe may be inaccessible without being unreal. The interior of a black hole may be hidden from an outside observer without being absent from spacetime. Past events are not merely distant places, so these comparisons have limits. Yet they reveal the logical gap at the center of the mystery. What cannot be reached may be gone, or it may remain part of reality in a form that does not permit return. The present offers no simple test. Every piece of evidence about the past is itself a current physical arrangement. A photograph is a pattern of pigment or pixels. A fossil is mineral structure. A memory is activity and organization within the brain. A crater is a deformation in rock. Ancient light is an electromagnetic field arriving now. These records allow earlier events to be reconstructed, sometimes with remarkable precision. But they do not contain those events in full. A photograph of a storm does not preserve every detail of the air, sound, motion, and experience surrounding it. A fossilized bone does not retain the entire animal or landscape. Records survive because some features of an event leave stable effects while most details disperse. This selectivity helps explain why the past feels both dense and empty. It is dense because the present is saturated with inheritance. Every atom has a history. Every orbit is shaped by earlier motion. Every organism carries structures produced by previous generations. The current universe is impossible without its prior states. At the same time, the past is empty because most of those states cannot be recovered in complete detail. Heat spreads. Waves interfere. Objects erode. Signals weaken. Information becomes mixed into larger systems. The present carries the past forward, but often in forms too scattered to reverse. The difference between influence and survival therefore becomes essential. An event may remain influential without remaining present. A volcanic eruption can alter climate long after the eruption ends. A supernova can seed future stars with heavy elements after the star itself has vanished. A decision can shape decades of consequences, even when the moment of choosing is irretrievable. Effects preserve structure, but not necessarily existence. The world may be causal without being archival. It may remember enough to continue while forgetting almost everything required to reconstruct what happened. Physics complicates even this restrained conclusion. The equations used to describe motion do not usually include a command that older moments must be erased. They describe relations among events, changes, fields, and trajectories. In many formulations, an event that occurred remains part of the mathematical description, just as a location remains part of a map after a traveler has left it. The map does not claim that all locations are experienced at once, but it does not delete places that are no longer occupied. This points toward a more unsettling possibility. Perhaps time does not behave like a substance flowing past and carrying moments into nothingness. Perhaps the sense of passage belongs partly to the way conscious systems encounter a larger structure. That possibility should not be accepted too quickly. Mathematics can represent what happened without granting ongoing existence to the event itself. A calculation may contain earlier values because the model needs them, not because nature preserves them as living regions of reality. A historical record can include a battle without making the battle still occur. Description and existence cannot be treated as identical. The central question, therefore, remains open. When a moment passes, does the universe remove it? Or does experience simply move beyond it? Ordinary life offers no decisive answer because it is organized around access. The present is what can be acted upon. The past is what can be remembered or inferred. The future is what can be anticipated but not known in the same way. These practical differences create the emotional reality of time. Loss matters because moments do not return. Change matters because earlier arrangements cannot simply be resumed. Whether the past still occupies some deeper structure does not restore access to it. A vanished childhood, an extinct species, or a dead star remains unreachable in the form it once had. The mystery begins precisely there, between physical description and lived experience. The past may be gone in the only sense that matters to action, while still remaining part of reality in a sense that physics has not settled. Or it may survive only through traces, with no continuing existence beyond the records embedded in the present. The evidence does not yet force one answer. It only reveals that the familiar belief in a disappearing past rests on more than observation. It rests on the structure of memory, the limits of perception, and the deep habit of treating the present as the only moment that is fully real. Before that habit can be tested, time itself must be given a clearer shape. And the first shape offered by physics is the old idea of a universal clock, moving evenly through a universe in which every event shares the same now, long before time became tangled with motion, gravity, and the speed of light. Physics treated it as the quiet background against which everything else changed. In the classical picture associated with Isaac Newton, time does not belong to any particular object. Observe, planet, or star. It proceeds evenly on its own, the same everywhere, unaffected by what moves within it. A pendulum may swing, a planet may orbit, a stone may fall, and a human heart may beat. But all of these processes unfold inside a single universal duration that would continue even if no clock existed to measure it. This idea is so close to ordinary experience that it can feel less like a theory than a description of reality itself. Events happen one after another. Some are earlier, some are later, and some occur at the same time. In principle, every event in the universe can be placed into one shared order. The past lies behind the present, the future lies ahead, and the present forms a thin boundary moving through the whole cosmos at once. Under this view, asking whether the past still exists appears almost unnecessary. Time advances, moments pass, and what has passed is no longer present. The structure feels clean because the clock is common to everything. Newtonian time supports this intuition by separating time from the contents of the universe. Space provides where, time provides when, and neither depends on the observer. A clock on Earth and a clock carried to a distant star are assumed to participate in the same underlying flow. They may be built differently or run imperfectly, but their errors belong to the instruments. not to time itself. Beneath all measurements, there is presumed to be one correct cosmic time. This hidden standard gives classical mechanics its clarity. If the position and velocity of an object are known at one moment, the laws of motion determine how its state changes at later moments. Every part of the calculation refers to the same temporal parameter. The planets do not each carry private versions of now. Their motions can be compared because the equations place them on a shared temporal stage. The elegance of this framework is difficult to overstate. It allows falling bodies, projectiles, tides, moons, and planetary orbits to be described as parts of one ordered system. It also fits the scale of life in which human intuition develops. At ordinary speeds, the differences later revealed by relativity are so small that they disappear beneath the precision of everyday clocks. Two people walking past one another agree almost perfectly about the order and timing of nearby events. A train arriving at a station, a bell sounding, and a door opening can all be assigned times without any practical need to ask how the observer is moving. Light travels so quickly across familiar distances that vision gives the impression of immediacy. A room appears to share one present. A city appears to share one present. By extension, the mind imagines that the universe does as well. This is not a foolish mistake. It is an accurate approximation under the conditions most often encountered. Classical time works because the world of human-scale motion is slow compared with light, and gravitational differences are usually too modest to disturb daily experience. Within that narrow range, clocks can be synchronized, schedules can be trusted, and events can be arranged as though simultaneity were obvious. The deeper commitment appears only when this local success is extended without limit. If one universal time exists, then distant events must have definite relationships of before, after, or simultaneous, even when no signal can connect them immediately. Somewhere, according to the classical view, there is a true answer to what is happening right now around a distant star. The information may take years to arrive, but the event itself belongs to the same present as a heartbeat on Earth. This imagined cosmic now is not something anyone directly observes. It is inferred from the assumption that time flows identically everywhere. The universe becomes a vast collection of changing things, arranged beneath one invisible clock. That picture also shapes the most familiar idea of disappearance. A universal present seems to sweep forward like a plane crossing all of space. Events enter that plane, become real, and then fall behind it into the past. The metaphor is powerful, even though classical mechanics does not require a literal moving surface. Once all observers share the same now, it becomes natural to treat the present as physically privileged. The past can then be understood as what the universal clock has left behind. Its effects may remain, but the moments themselves no longer occupy the active edge of reality. This is the background assumption hidden inside many ordinary statements about time. A building once stood where an empty field now lies. A star once burned where a remnant now expands. A species once lived where only fossils remain. The word once carries more than chronology. It suggests a change in ontological status, a movement from existing to no longer existing. Classical time makes that suggestion easy because the same temporal boundary applies to every object. Yet even within this model, the nature of passage remains elusive. A clock measures change by comparing one repeating process with another. It does not detect time as a substance. The hands move. Atoms oscillate, pendulums swing, and planets turn. From these changes, duration is constructed and compared. Newtonian physics assumes that an absolute time lies beneath them, but it does not explain what makes the present move or why one moment should cease to be real when another arrives. The equations describe how states evolve from one time to another, but the felt flow of time is not an extra force inside them. This distinction matters because the certainty of the classical picture comes partly from intuition rather than from direct detection. Absolute time provides a framework of extraordinary usefulness, but usefulness alone does not prove that nature contains the framework in the same form. For centuries, there was little reason to doubt it. The successes of classical mechanics were immense, and the idea of a shared time seemed woven into those successes. Astronomers could predict eclipses. Engineers could calculate trajectories. Navigators could use clocks and stars to determine position. The world behaved as though time were universal because, at the available precision and speed, nearly every test returned that answer. Even when light was understood to take time to travel, the delay did not yet destroy the deeper assumption. One could imagine correcting for the travel time and recovering what was truly happening at a distant location at the same universal moment. The signal arrived late, but the distant present was still presumed to exist in step with the local one. This confidence made the classical universe conceptually stable. Space could be large, but time tied it together. The present was not merely where awareness happened to be. It was a cosmic layer shared by all matter. The past was equally well defined, a completed sequence extending behind that layer, and the future waited ahead in the same ordering. Within such a structure, the question of whether the past remains real has a strong default answer. It does not. Only the current state of the universe fully exists, while earlier states survive through consequences, records, and memory. That view is often called presentism in philosophy. Though classical physics does not force every philosophical detail of it, what classical physics does provide is the temporal architecture that makes presentism feel natural: one time, one order, one present. The decisive challenge arrives when motion is no longer slow, distance is no longer modest, and the behavior of light is taken as a fundamental limit rather than an inconvenience to be corrected. Then the universal clock begins to fail, not because clocks are poorly built, but because nature does not preserve the single shared now that classical intuition expects. The old picture does not collapse through philosophical argument alone. It breaks when different observers, each reasoning correctly from the same physical laws, cannot agree on which distant events belong to the present at all. The first crack in the idea of a universal present does not come from a philosophical puzzle, but from the behavior of light. By the end of the 19th century, experiments and electromagnetic theory had converged on a result that resisted the expectations of classical mechanics. Light in a vacuum travels at the same speed for all inertial observers, regardless of how the source or the observer is moving. In ordinary life, speeds add. A person walking forward inside a moving train travels faster relative to the ground than a person standing still inside it. A ball thrown from the train carries the motion of the train as well as the motion of the throw. Light refuses to behave this way. Its measured speed remains fixed. To preserve that fact, something deeper has to give. And what gives is the old assumption that space and time are separate, universal backgrounds shared identically by everyone. Einstein's special theory of relativity begins from a restrained set of principles, yet their consequences reach directly into the meaning of past, present, and future. The laws of physics take the same form for observers moving at constant velocity, and the speed of light remains the same for each of them. These statements do not merely change the equations used for fast-moving objects. They change what counts as simultaneous. Consider two flashes of light produced at different places. An observer positioned midway between them may receive both flashes at the same moment and conclude that the emissions occurred simultaneously. Another observer moving toward one source and away from the other will still measure each light beam traveling at the same speed. Because the observer moves toward one flash and away from the other, the signals arrive at different times. In classical reasoning, this could be corrected by adding the observer's motion to the speed of the light, restoring a single underlying order. Relativity does not permit that correction. The measured speed of light does not adjust. The disagreement about arrival cannot be separated from a disagreement about simultaneity itself. Two observers can therefore assign different times to distant events without either making an error. Their clocks can be perfect. Their calculations can be correct. The difference lies in the structure of spacetime, not in the quality of observation. This is the relativity of simultaneity, and it removes the foundation beneath a cosmic now. Nearby events remain easy to order when one can influence the other. If one event sends a light signal that reaches another, all observers agree that the cause comes before the effect. No change of motion can reverse that causal sequence. But distant events, separated in such a way that no signal, traveling at or below the speed of light can connect them, occupy a more uncertain relationship. One observer may judge them simultaneous. Another may place the first before the second. A third may reverse that order. The universe does not provide a single preferred answer for which of those distant events belongs to the present. The word now becomes local rather than universal. It refers to an event along an observer's path, not to a complete slice extending through all space with absolute authority. This is not because information travels slowly and observers are waiting for delayed news. Even after every travel delay is calculated, the disagreement remains. It is built into the way space and time coordinates transform between moving frames. An observer on Earth and an observer passing at high speed can construct different surfaces of simultaneity, different sets of distant events assigned to the same moment. Neither surface is the hidden true present. Special relativity treats both as valid descriptions. The effect is negligible at the speeds of daily life, which is why ordinary intuition remains so stable. Walking, driving, and even orbiting Earth produce differences too small to notice without precise instruments, at velocities approaching the speed of light. However, the mismatch becomes large. Time intervals stretch. Lengths contract along the direction of motion, and clocks following different paths no longer accumulate the same amount of elapsed time. These are not visual illusions. Fast-moving particles survive longer in laboratories than they would at rest. Atomic clocks flown on aircraft or carried by satellites do not remain perfectly synchronized with clocks left on the ground. Relativity appears in actual measurements and in technologies that must correct for it. Yet time dilation, striking as it is not the deepest challenge to the disappearing past. The sharper challenge comes from simultaneity. If there is no single present shared across space, then the boundary separating what exists from what no longer exists becomes difficult to define. Suppose a distant event is considered present in one observer's frame, but past in another. If only the present exists. Which observer's present determines reality. Choosing one frame would introduce a preferred state of motion that special relativity does not reveal. Treating every observer's present as equally real seems to enlarge reality beyond one universal instant, because the collection of those presents includes events that other observers call past or future. This argument motivates the block universe interpretation, but it does not by itself prove it. Relativity constrains the structure of temporal relations. It does not directly announce which events possess existence. The move from physical symmetry to metaphysical conclusion requires interpretation. Still, The old picture of a present sweeping through the cosmos loses its natural privilege. No experiment within special relativity identifies a universal layer of reality advancing from future to past. There are only events, intervals, causal connections, and observer-dependent divisions of space-time into space and time. Even the passage of time becomes more personal in a precise physical sense. Each object carries its own proper time, the duration measured by a clock traveling with it. Two clocks that separate, move differently, and reunite may show different elapsed times. Their disagreement is not a failure to track an invisible master clock. It is the expected result of following different paths through spacetime. This gives every body a local temporal history. A planet, a spacecraft, a particle, and a person each move along a route whose measured duration belongs to that route. The universe still preserves order where causation demands it, but it no longer arranges all distant events under one shared temporal label. That distinction matters for the status of the past. In the Newtonian picture, the past can be imagined as the region already crossed by a universal present. In relativity, there is no universal crossing line. An event that is securely in the causal past of another remains earlier for all observers. But many distant events do not fit into a single absolute order. The categories of past and future become partly dependent on location and motion, bounded by the paths along which light and influence can travel. This does not mean that anything can happen in any order. Relativity is not temporal chaos. Causal structure is strict. Events connected by signals or material influence preserve their sequence. A star must emit light before a telescope receives it. A particle must be created before it decays. A message cannot arrive before it is sent in any ordinary relativistic frame when it travels within the light speed limit. What relativity removes is not order itself, but the universal ordering of events too widely separated to affect one another at that moment. The result is a universe less like a stage under a single clock and more like a network of local histories connected by light. Each observer carries a valid account of nearby time, and those accounts fit together through exact mathematical relations. But they do not merge into one preferred present. Human experience remains narrow enough to conceal this structure. Biological memory still points backward. Clocks in the same room still agree almost perfectly. The sense of a common now survives because the region of daily life is small and slow. Yet physics does not extend that convenience to the whole cosmos. Once simultaneity becomes relative, the question of whether the past has disappeared can no longer be asked as though everyone agrees on where the past begins. The universe may not contain a single frontier, separating what is real from what has ceased to be. It may instead contain a four-dimensional arrangement in which observers divide events into space and time differently while preserving the same underlying relations. Einstein's theory does not force that conclusion, but it opens the door by removing the one structure that made disappearance seem simple. The absolute present is gone, and with it goes the clean idea of a universal moment that erases everything behind it. Minkowski's spacetime begins with a change in what an event is. In ordinary thinking, an event is something that happens somewhere at a particular time, as though space and time were two separate labels attached to the same occurrence. Relativity binds those labels together. A flash of light, a collision between particles, the birth of a star, and the fall of a raindrop are each represented by a single location in a four-dimensional structure called spacetime. Three coordinates describe where the event occurs, and one coordinate describes when. Different observers may divide this structure into space and time in different ways, but they do not disagree that the event itself occupies a definite place within it. This geometrical shift does not make time identical to space in every respect. Motion through time cannot be changed as freely as motion through space, and the causal order between connected events remains protected. Yet space and time are no longer independent backgrounds. Together, they form the arena in which physical history is written. The importance of this idea lies not only in calculation, but in what it permits the past to become. In a purely present-centered picture, reality resembles a stage that is constantly replaced. One complete arrangement of the universe exists, then gives way to another, while the earlier arrangement disappears. In spacetime geometry, the description is different. Events are not treated merely as temporary states that vanish after occurring. They are assigned positions within a larger structure. The explosion of a distant supernova, the formation of Earth, and the movement of a hand across a table occupy different spacetime locations. Just as cities occupy different locations on a map, no observer stands outside spacetime to see the whole arrangement at once. But the mathematics does not remove earlier events when later ones occur. It relates them. A map analogy helps only to a point. Paris and Cairo can coexist as places even when a traveler visits one and not the other. By contrast, an earlier moment cannot be reached simply by changing direction. The geometry of spacetime contains limits absent from an ordinary map. Light cones separate events that can influence one another from those that cannot. Massive objects follow paths that remain within those limits. The past is therefore not another region of space waiting nearby. Still, the comparison reveals why the language of disappearance becomes less obvious. If an event is a location in spacetime, then its being earlier does not automatically mean its coordinates are erased. The structure includes temporal separation as part of its geometry. This was the insight developed most clearly by Hermann Minkowski, who reformulated special relativity as a theory of four-dimensional spacetime, what one observer calls a distance in space and an interval in time. Another observer in motion may divide differently, yet both agree on a combined quantity called the spacetime interval. This interval remains invariant, meaning that all inertial observers calculate the same underlying separation even when they disagree about its spatial and temporal parts. The invariance is not merely a useful trick. It indicates that spacetime has an observer-independent structure beneath the changing coordinates. A single event does not move between existence and non-existence because an observer chooses a different frame. Its place in the structure remains fixed, while the observer's classification of distant events into simultaneous, earlier, or later changes. The geometry therefore preserves more than any one perspective can display. Each observer constructs a slice of events judged simultaneous, but another observer constructs a tilted slice through the same spacetime. Neither slice is the whole structure. If reality were restricted to one observer's present, it would exclude events included in another observer's present. Spacetime geometry avoids that conflict by treating the underlying network of events as more fundamental than any particular division into now and not now. This is one reason the block universe interpretation feels natural within relativity. The four-dimensional manifold, meaning the continuous mathematical space used to represent all events, can be understood as containing the full history of the universe. A galaxy's formation, its later collisions, and its eventual fading would occupy different regions of that manifold. Nothing in the geometry itself marks one thin layer as uniquely real. There is no glowing boundary labeled present. There are only local events and the relations among them. Yet caution is necessary. A mathematical representation can include the past without settling whether the past exists in the same sense as the current moment. Historians place events on timelines, and engineers place earlier states into simulations. But the presence of an event in a model does not prove its continued physical reality. The spacetime manifold may be interpreted as a complete ontology, a description of what exists, or as a formal device organizing the relations among events that occur and then cease. Relativity strongly constrains the form of any interpretation, but it does not speak in philosophical language. The equations identify intervals, trajectorias, and causal structure. They do not declare whether all regions of the manifold possess equal existence. Even so, the geometrical picture changes the burden of explanation. Under absolute time, the disappearing past seemed effortless because a universal present could sweep forward. Under relativity, any theory that grants existence only to the present must explain which present is meant. A preferred slicing of spacetime could be introduced, but special relativity supplies no observable reason to choose one inertial frame over another. General relativity complicates the issue further because spacetime itself can curve, and in many cosmological models, there may be natural ways to define large-scale time. These cosmic time coordinates are useful, especially in universes that are approximately uniform on the largest scales. But they do not restore Newton's absolute clock in a universal and fundamental form. They depend on the geometry and matter distribution of a particular spacetime. The four-dimensional view, therefore, remains more than a convenient diagram. It expresses the fact that temporal measurements depend on paths and observers while spacetime relations remain consistent. Gravity deepens this structure. In general relativity, matter and energy shape spacetime geometry, and that geometry guides the motion of matter and light. A planet orbits not because it is pulled across a fixed stage by an invisible force in the Newtonian sense, but because it follows the curved structure around a massive body. Clocks closer to a strong gravitational field accumulate less proper time than clocks farther away. The rate at which time passes is therefore not laid uniformly over the universe. It belongs to the geometry itself. This makes the idea of a single moving present even harder to preserve. Different paths through curved spacetime contain different amounts of elapsed time, yet they remain parts of one connected structure. A past event can influence a later event through signals, particles, or gravitational effects, because the geometry links them causally. A supernova enriches interstellar gas. That gas becomes part of a later star. Material from that star enters a planetary system. The earlier explosion is not present as an active event, but its location in spacetime remains linked to later locations by continuous chains of influence. The geometry records, not a memory in the psychological sense, but a pattern of relations that cannot be described without the earlier event. Removing it would not merely erase a story. It would break the causal structure leading to the present. Yet this does not mean that the explosion is still happening. In the spacetime picture, happening is local. An event does not continue across all time. It occurs at its own position. The claim that the past still exists, if it is made, does not mean that past processes are ongoing from the standpoint of the present. It means that their spacetime locations are no less part of the total structure than later ones. This distinction prevents the block picture from becoming a confused image of every event occurring simultaneously. Simultaneity is precisely what relativity has made observer-dependent. The four-dimensional structure is not one enormous present. It is a pattern in which different events stand in temporal and causal relations without needing to be brought into a single now. Human awareness follows only a narrow sequence within that pattern. It encounters one local event after another, storing partial records of earlier ones and anticipating later ones. From inside that sequence, time feels as though it advances, and the world continually renews itself. From the geometrical perspective, The sequence itself becomes a path through spacetime. The past then appears not as a collection of moments thrown away, but as earlier locations along the same continuous history. Whether those locations possess enduring reality remains an interpretive question, but spacetime gives the question a precise shape. The mystery is no longer whether memories are strong enough to preserve what happened. It is whether a physical event, once assigned a place in the geometry of the universe, ever needs to be removed from that geometry at all. A muon created high in Earth's atmosphere begins with a lifetime so brief. In an ordinary classical picture, many of these particles should decay before reaching the ground. Yet, detectors at the surface regularly record them. The explanation is not that the particles disobey their own clocks. It is that motion through spacetime gives each muon a particular history. And along that history, the amount of elapsed proper time is smaller than the time measured by observers on Earth. This path is called a world line. It is not a trail left behind in space like a mark across sand. It is the complete sequence of events occupied by an object as it moves through spacetime. Every particle has one. Every planet has one. Every living body has one. A world line begins wherever the object's history begins and extends through every event that belongs to that history, linking positions in space with moments in time. In a spacetime diagram, an object at rest does not remain a single point, because rest in space is still motion through time. Its world line rises through the temporal dimension while its spatial position stays constant. An object moving through space traces a tilted line, and light follows paths at the limiting angle permitted by causality. The shape of the line records motion. Its length, measured according to spacetime geometry rather than ordinary spatial distance, records proper time. This makes a world line more than a convenient graph. It is the physical history of an object expressed as geometry. A human life can be represented in the same way, though the full line is vastly more complicated than a clean diagram suggests. It begins with a chain of biological events, passes through every heartbeat, motion, sleep cycle, and change of location, and continues until that organized life ends. At no stage does the entire line become visible to the person whose history it describes. Experience occupies one local event after another. Memory contains compressed traces of earlier portions, while expectation projects possible later portions. The world line itself, however, allows physics to represent all of those events as belonging to one continuous path. The earlier childhood event, the current bodily state, and a later movement are not separate objects. They are different locations along the same history. This is why world lines sharpen the question of whether the past disappears. If an object's history is a path through space-time, then its past is not merely a collection of vanished states. It is the earlier segment of the path that leads to the current event. The geometry does not need to recreate that segment each time it is discussed. It is already part of the structure used to define what the object is and how it arrived where it is. Yet the line should not be mistaken for a film strip being watched from outside the universe. No physical observer stands beyond spacetime, seeing an entire life or orbit at once. A world line is a representation of relations among events, and whether every portion of that representation exists equally is still an interpretive question. Even so, the concept changes the way persistence is understood. In ordinary language, an object seems to endure by remaining the same thing while time passes around it. Relativity reverses the emphasis. The enduring object can be understood as the extended history itself. While each momentary state is only one cross-section through that history, a planet is not merely the sphere occupying its current orbit. Its full physical identity includes a continuous trajectory through billions of years of spacetime. Earth's path curves around the sun, while the Sun follows its own course around the center of the galaxy. The planet's history is a woven route through a changing gravitational geometry. Earlier Earth, with different continents, climates, and living forms, lies along the same world line as the present planet. Though the planet's material composition and internal structure change continuously, a world line, therefore, does not imply that an object possesses an unchanging essence. It provides continuity through change. The same is true at smaller scales. An atom in a living cell may once have been part of seawater, volcanic gas, interstellar dust, or an ancient organism. Its route through spacetime crosses environments and systems, joining and leaving structures whose own histories overlap with it. The universe becomes a dense web of world lines rather than a sequence of isolated cosmic snapshots. At every interaction, paths meet. A photon leaves a star and ends at a detector. Two particles collide, and new paths begin. Matter falls into a black hole and crosses a horizon. A signal passes between spacecraft and Earth. Causation is written in these intersections. One event influences another because a physically permitted path connects them. This gives the past a precise role. The past is not simply whatever is remembered. It is the set of earlier events linked to the present by causal world lines. Some of those connections are direct. Light from a star reaches a telescope. Others are distributed through countless intermediate interactions. The oxygen in an atmosphere reflects ancient biological activity, while heavy elements in rock-record stars that died before the solar system formed. The present event sits at the meeting point of histories extending backward through space-time. World lines also reveal why different observers can age differently without contradiction. Consider two clocks that begin together, separate, and later reunite. One remains on Earth, while the other travels at high speed before returning. Their world lines connect the same departure and reunion events, but follow different routes between them. Space-time geometry assigns different amounts of proper time to those routes. The traveling clock may record less elapsed time. Neither clock is wrong, and there is no hidden universal duration that both failed to measure. Their histories simply contain different temporal lengths. This is the core of the twin effect often used to illustrate relativity. The decisive fact is that the two observers trace different world lines through space-time. Proper time belongs to the path. This makes personal history physically local. There is no single quantity of elapsed time that every possible observer must experience identically along every route. Near strong gravity, world lines diverge in elapsed time even more sharply. A clock close to a massive body accumulates less proper time than a clock farther away. Around a black hole, the contrast can become extreme. Again, no master clock settles the disagreement. The geometry of each path does. These effects turn history from a universal sequence into something carried by objects themselves. Each world line has its own succession of local moments. The object encounters events in order along that line, and that order cannot be reversed for any material observer. A person cannot step sideways from one point on a world line into an earlier point as though moving between rooms. The path is constrained by the local light cone, and ordinary matter proceeds toward the future direction defined along it. Representing earlier events geometrically does not create a method for returning to them. A road shown on a map may be traveled in either direction, but a time-like world line is not an ordinary road. Its temporal orientation is tied to causality, physical processes, and the accumulation of proper time. If the past remains part of a world line, it does not follow that a conscious observer can revisit it. Existence, if granted to earlier segments, is not the same as accessibility. The child state and adult state of one person may belong to the same extended history without being mutually reachable. The adult contains records shaped by the child, but the adult cannot redirect the present world line into the already occupied earlier segment under normal physical laws. The history is continuous, precisely because those events occur in their order. A world line also complicates the idea that only the present version of an object is real. If reality consists only of a moving instant, then the object at each moment must somehow inherit identity from states that no longer exist. Physics can describe that inheritance through laws connecting successive states. But relativity offers another image. The object is the whole temporally extended pattern, and the present state is merely the local part encountered now. Whether nature truly contains objects as complete four-dimensional histories cannot be read directly from the diagrams. World lines are indispensable to relativity, but the metaphysics of their segments remains open. A presentist can treat the line as a record of what existed and what may exist, granting full reality only to the current event. A block universe interpretation can treat the entire line as equally embedded in spacetime. The equations support the structure used by both positions while refusing to identify one moment as a universal present. What they do establish is that no physical history can be reduced to a sequence governed by one cosmic clock. Every object carries duration along its own route, and every current state is attached to earlier events by an unbroken causal path. The past is therefore not an abstract warehouse of memories. It is the preceding geometry of everything that exists now. The unanswered step is whether this geometry merely describes a history that has vanished, or whether the history, complete from beginning to end, is the object itself. The block universe begins not with the claim that every moment is happening at once, but with the quieter idea that happening belongs to locations within spacetime rather than to a single cosmic present moving across them. In this interpretation, the universe is a four-dimensional structure containing events ordered by their spatial, temporal, and causal relations. The formation of a star, the cooling of a planet, the first movement of a living cell, and the reading of a clock each occupy different regions of that structure. Past, present, and future are names assigned from the standpoint of an observer located at one event and moving along one world line. What is past lies earlier along the relevant causal order. What is future lies later. What is present is local, a point or small region of immediate experience, not a universal layer shared by the whole cosmos. This picture is often called eternalism because it treats events at different times as equally part of reality, though not equally accessible. The word eternal can mislead if it suggests endless duration or continuous repetition. The claim is not that every event lasts forever. A supernova still occurs at one set of spacetime locations. A heartbeat still has a beginning and an end. An extinct species still occupies a finite interval in Earth's history. The proposal is that these events do not need to be erased from reality merely because other events lie later along a world line. Their existence is positional rather than temporary. A mountain is not unreal because it is distant. In the same spirit, an earlier event would not be unreal simply because it is temporally separated. Yet time is not merely another direction that can be crossed at will. So, the analogy remains incomplete. The structure may contain an event without granting later observers any route back to it. The block universe, therefore, separates two ideas that ordinary experience blends together, whether something exists and whether it can be reached. The past may remain part of spacetime, while remaining permanently inaccessible from the present. Nothing is restored by this. No lost moment becomes available again. The child does not return because the adult's world line still includes childhood. A dead star does not resume burning because its earlier stages remain part of the cosmic geometry. Each event occupies its own place and stands in fixed relations to others. From within the block, the sequence still matters. Causes precede effects along permitted paths. Clocks accumulate proper time. Bodies age. Stars exhaust fuel. Entropy rises in the direction experienced as the future. The block does not flatten all history into one undifferentiated instant. It preserves change by embedding differences between temporal regions. An object is colder later than earlier. A planet occupies one orbit and then another. A living system develops, reproduces, NDs. The entire pattern may be fixed in the four-dimensional structure, but the changes within it remain real as relations between stages. The deeper tension concerns passage. Human experience does not merely register difference. It seems to encounter a present that advances, bringing new events into reality and leaving old ones behind. The block universe asks whether this feeling reflects a fundamental process in the cosmos or the internal organization of observers whose brains store records in one temporal direction. A conscious system at one event contains memories of earlier events but not later ones. It receives signals from the past light cone, updates its state, and forms expectations about what lies ahead. At each stage of its world line, the system has a local sense of now. Nothing in that description requires a universal present to move. The sequence of conscious states is already arranged along the world line. Each state contains the records appropriate to its location. The impression of passage may then arise from the asymmetric structure of memory and causation rather than from time itself flowing. This does not reduce experience to illusion in the ordinary sense. Pain, anticipation, recollection, and change remain genuine features of physical and conscious life. What may be illusory is the additional belief that the whole universe shares the same advancing present. The block interpretation gains support from relativity because relativity denies a preferred division of spacetime into universal slices of now. Observers in different states of motion disagree about which distant events are simultaneous, yet they agree on the deeper spacetime structure. If reality consisted only of one absolute present, the theory would seem to require a hidden rule, selecting one observer's slicing over another. The block universe avoids that problem by treating all events in the manifold as part of reality, regardless of how different observers divide them into past, present, and future. The interpretation is economical because it grants priority to the invariant structure rather than to any observer-dependent surface of simultaneity. Still, economy is not proof. A theory may describe spacetime as a complete mathematical object without requiring every represented event to exist in the same ontological sense. The equations can encode what happened, what is happening, and what will happen without deciding whether all three categories are equally real. The block universe is therefore a philosophical interpretation shaped by physical evidence, not an experimental result stamped directly onto a detector. Its strongest case is indirect. Relativity removes the universal present. World lines organize histories geometrically, and spacetime models often represent entire solutions at once. Together, these features make a four-dimensional reality coherent and natural. They do not compel it beyond dispute. The interpretation also raises difficult questions about freedom and uncertainty. If future events are already part of spacetime, then the future appears fixed in the same sense as the past. Every decision would occupy a later region of a world line, and every outcome would already have its place in the block. This can sound like fatalism, but the concepts are not identical. A decision may be part of the structure precisely because the physical system makes it through deliberation. Memory. motive, and response. The event is not forced by an external script merely because it has a location in spacetime. Within the block, causes still operate through local processes. A choice can remain causally effective even if the entire history is represented as a completed geometry. What changes is the idea that alternatives enter existence from a genuinely open future. Whether fundamental physics supports such openness is a separate question, complicated by quantum theory. Quantum probabilities may describe genuine indeterminacy, incomplete knowledge, branching outcomes, or something else. Depending on interpretation, a block universe can be adapted to several of these possibilities, but none turns the metaphysical question into a settled fact. The block may be single and fixed, may contain branching structures, or may fail as a complete picture if time is more fundamental and dynamic than relativity alone suggests. There is also the problem of becoming. Some philosophers argue that change requires more than differences between earlier and later regions. They hold that events genuinely come into existence, and that a static four-dimensional description leaves out the transition from possibility to actuality. Defenders of the block reply that no extra cosmic process is needed. Change is present whenever an object has different properties at different times. The disagreement reaches beyond measurement because both sides can accept the same relativistic predictions while interpreting their meaning differently. What physics contributes is a constraint. Any account of a privileged present must fit a universe in which simultaneity depends on motion, and no ordinary experiment reveals a single cosmic. Now, the block universe meets that constraint cleanly. Its cost is that the flow of time, so immediate in experience, no longer appears as a fundamental feature of the universe. It becomes a feature of perspective, memory, and ordered physical processes within the block. Under this view, the past never disappears because disappearance was never part of the underlying geometry. Events do not move out of existence. Observers move along world lines, carrying records of earlier regions and no direct knowledge of later ones. The present becomes similar to here, a real location for the observer, but not a privileged boundary dividing reality from unreality everywhere else. Yet the phrase "move along" must also be handled carefully. A complete world line does not literally slide through space-time under the control of another time. Introducing such motion would require a second temporal dimension to measure the movement, and then the same question would begin again. The block picture instead treats the observer's succession of states as internal to the world line itself. Each state is linked to the next by physical processes, and each contains the sense of occupying the present. The universe need not update from outside. Its history is the ordered totality. This is the boldest answer to the mystery of the vanished past. The past does not survive as a hidden archive, a ghostly copy, or a realm waiting to be reopened. It remains exactly where it always was, as an earlier region of space-time. But that answer carries no final authority merely because it fits relativity well. The same equations still leave room for rival views in which only the present exists, or in which reality grows as new events are added. The block universe changes the question from whether traces preserve the past to whether space-time itself requires anything to vanish. And the next difficulty is that physics has not yet decided how that requirement should be interpreted. A space-time diagram can look more decisive than it is. Once past, present, and future events are drawn together within one four-dimensional geometry. The page seems to contain the answer before any argument begins. The earlier event remains on the diagram. The later event remains on the diagram. No line is erased when another is added. From that visual structure, the block universe can appear not merely plausible, but unavoidable. Yet a diagram represents relations among events. It does not, by itself, determine which represented events exist in the fullest philosophical sense. This is where physics and interpretation separate. Relativity tells observers how measurements of time and space depend on motion, how light constrains causation, how clocks accumulate proper time along different world lines, and why no universal present is revealed by the theory. These are physical claims tested through experiment. The further claim that past and future events are equally real is an interpretation of what the formalism means. It may be the most natural interpretation for some physicists and philosophers, but naturalness is not the same as proof. The distinction matters because the mystery of the past turns on the meaning of existence, not merely on the placement of coordinates. Special relativity weakens the classical picture of a single present shared across the universe. Observers in relative motion divide spacetime into different sets of simultaneous events, and no ordinary experiment singles out one division as the true one. This creates a serious difficulty for presentism, the view that only present events exist. If the present is different for different observers, then presentism must explain whether existence itself depends on the observer, whether one hidden frame defines the real present, or whether the concept of present reality needs to be reformulated. The block universe avoids these problems by granting reality to the entire space-time structure. All observers then describe different slices through the same collection of events. Their disagreement concerns coordinates, not existence. This elegance is one of the strongest reasons to take eternalism seriously. It respects the symmetry of the theory and introduces no preferred cosmic frame that experiments have failed to detect. Even so, a difficulty for one interpretation is not an experimental confirmation of another. Physics often allows multiple pictures that agree on all measurable outcomes. The disagreement then concerns what the equations are about rather than what numbers they predict. A presentist may accept every relativistic effect while proposing that reality possesses an objective becoming not captured by the coordinate description. Such a view might introduce a preferred foliation, a special way of dividing spacetime into successive spatial layers, even if that foliation cannot be observed directly. This addition may appear inelegant because it supplies hidden structure beyond what relativity requires. But logical possibility and physical proof are different standards. The absence of evidence for a preferred present counts against the idea without strictly showing that no such structure exists. General relativity makes the situation more complicated rather than simply closing the case. In some cosmological models, matter is distributed on large scales in a way that allows a useful cosmic time to be defined. Observers moving with the average expansion can treat certain large-scale slices as surfaces of equal cosmic age. This is not Newtonian absolute time. It depends on the particular geometry and matter content of the universe, and it may fail in more irregular spacetimes. Still, it gives presentist or growing block interpretations a possible structure to use. The existence of a convenient cosmic slicing does not establish that the slice is metaphysically privileged, but it prevents the debate from ending with the simple statement that relativity permits no meaningful global time under any circumstances. The physical theory is subtler. Some spacetimes can be organized globally in clear ways. Others resist such organization. The ontology does not fall directly out of the coordinate system. A second alternative is the growing block universe. In this view, past and present events exist, but future events do not yet exist. Reality forms a four-dimensional block whose boundary advances as new events become actual. This interpretation preserves the past rather than erasing it, while also preserving a genuine sense of becoming. The universe is not complete from beginning to end. It accumulates history. At first, this appears to match experience more closely than eternalism because events seem to arrive and then remain settled. The past is fixed, the present is active, and the future is open. Yet, the growing block faces its own relativistic difficulty. A growing boundary needs a definition of which events are being added together. Without absolute simultaneity, it is not obvious how the edge of reality extends across distant regions. A preferred slicing could again be introduced. But the theory of relativity does not clearly identify one as fundamental. The view therefore retains becoming at the cost of extra structure or a more complex account of local growth. There are also versions of temporal ontology that avoid treating reality as one simple block or one universal present. Some proposals define existence through causal relations, allowing reality to grow locally along light cones rather than across a single cosmic surface. Others treat past, present, and future as concepts tied to events and observers without reducing them to mere psychology. These views attempt to preserve an objective distinction between what has happened and what has not, while respecting relativistic causality. Their variety reveals the central point: relativity narrows the available options, but it does not reduce them to one. Any acceptable account must explain observer-dependent simultaneity, invariant causal order, and the path-dependent accumulation of time. Several metaphysical frameworks can attempt that task. The block universe remains powerful because it does so with unusual simplicity. It treats the spacetime manifold used by the theory as the basic reality and avoids adding an invisible moving present. But simplicity is a principle of theoretical judgment, not a detector reading. The equations themselves do not contain a variable for being real. They assign physical quantities to events and connect those quantities through laws. They can tell whether two events are time-like, light-like, or space-like separated. They can determine whether one event can causally influence another. They can calculate the proper time along a world line and the curvature produced by matter and energy. They do not specify whether an event classified as future already exists or whether an event classified as past continues to exist after it occurs. Those statements belong to the interpretation placed around the mathematics. This does not make them meaningless. Interpretation guides what counts as an explanation. What kinds of theories seem natural, and which unanswered questions appear fundamental? It simply means that the authority of experiment reaches the structure of temporal relations more directly than the metaphysics of temporal existence. Quantum theory adds another layer of uncertainty. In some interpretations, future outcomes are not fixed before measurement or interaction. In others, the wave function evolves deterministically, while observers become correlated with different outcomes. A single fixed block can be made compatible with deterministic laws, but quantum indeterminacy may suggest a branching structure, a growing history, or a more relational account of events. None of these possibilities has produced a universally accepted picture of time. The combination of relativity and quantum theory remains incomplete at the deepest level, especially where gravity must be quantized. It would therefore be premature to treat one spacetime ontology as finally established when the underlying physical framework is itself unfinished. Even within classical relativity, the status of an event depends on questions the theory was not designed to answer. Physics asks what observers measure and how events are related. Metaphysics asks what kinds of things exist and whether existence changes. The subjects overlap, but they are not identical. A successful interpretation should respect the physics without pretending that the physics has spoken more clearly than it has. This restraint becomes especially important when considering the title question. The claim that the past never disappeared could mean several different things. It could mean that past events remain represented in a complete space-time manifold. It could mean that they continue to exist as regions of reality. It could mean that information about them persists in present records. It could mean that their causal influence remains embedded in later states. These statements are not equivalent. Relativity strongly supports the first and gives precise form to the fourth. It is compatible with the second, but does not prove it. The third belongs to the physics of records, memory, and entropy, rather than to space-time geometry alone. Confusing these meanings turns a careful possibility into a false conclusion. The most defensible position is therefore neither that the block universe has been demonstrated, nor that it is merely fantasy. It is a serious interpretation motivated by the structure of relativity, especially by the absence of absolute simultaneity and the geometrical treatment of world lines. Rival views carry heavier burdens. But burden is not disproof. The equations leave the universe open to more than one account of temporal existence. And that openness is not a weakness in physics. It marks the boundary between what measurement has settled and what the same measurements still allow reality to mean. The oldest light reaching Earth does not arrive from a place that is simply far away. It arrives from an earlier condition of the universe. Distance and time are bound together because every signal needs time to travel, and no physical influence moves faster than light in a vacuum. This limit creates a precise structure around every event in spacetime. From any chosen event, light can be imagined spreading outward in all spatial directions. In a spacetime diagram, those possible light paths form the surface of a cone. The upper half marks events that light from the present could reach later. The lower half marks events whose light could arrive at the present now. These regions are called the future light cone and the past light cone. They are not objects suspended in space. They describe the causal limits of an event, separating what can exchange influence from what cannot. The past light cone contains every earlier event capable of sending a signal to the present location. A nearby lamp, switched on a moment ago, belongs to it. So does the surface of the sun as it was roughly 8 minutes earlier. So do distant stars in states they occupied centuries or millennia ago. And remote galaxies as they appeared millions or billions of years before the current moment on Earth. Observation, therefore, reaches into the past by its ordinary nature. A telescope does not see a distant galaxy as it exists now in some universal sense. It receives photons emitted along earlier portions of that galaxy's history. The deeper the view extends into space, the earlier the observed region becomes. Astronomy is built from this delay. This fact can make the past seem physically present in a direct way. Ancient light enters a detector now. A supernova that occurred long ago can brighten a telescope tonight. The microwave background carries information from an era when the universe first became transparent to radiation. Yet the arrival of old light does not mean that the event itself has traveled forward intact. What arrives is a causal product of the event, shaped by its journey through expanding space, intervening matter, gravity, and the limitations of measurement. A photon emitted from a star can preserve information about the star's temperature, composition, motion, and magnetic environment, but it does not carry the star as a whole. The event remains at its own spacetime location. The signal connects that location to a later one. This distinction is the boundary between observing the past and returning to it. A telescope can receive what an earlier event sent outward, but it cannot reverse the causal path and place the observer inside the emitting event. The light cone points one way because the reception occurs later than the emission along every ordinary causal path. Information crosses from earlier events into later ones. The later event may record the earlier event, but the record does not become a passage back. The sun offers the simplest example. Its visible surface is always seen after a delay of about 8 minutes. If a sudden change occurred there, Earth would not register it until the corresponding light and other influences arrived. During that interval, the sun's current state would remain inaccessible from Earth. Yet even after the signal arrived, nothing about receiving it would move Earth back to the solar event. The delay can be measured and corrected in calculations, but it cannot be undone physically by observation alone. The same principle holds across greater distances. A galaxy observed as it was millions of years ago may have evolved, merged, dimmed, or changed beyond recognition during the time its light has traveled. The image arriving now is real, but it is not evidence that the earlier galaxy remains available as a destination in its earlier condition. Travel toward it would also take time, even at speeds approaching that of light. The traveler would follow a new future-directed world line and encounter later regions of the galaxy's history, not the regions seen in the old image. Moving through space toward an object does not move backward along the object's world line. The past light cone also reveals why there is no single observable past shared in the same way by every observer. Each event has its own cone. An observer elsewhere, or moving differently, occupies another event and therefore receives a different set of signals. The cones overlap, but they are not identical. What lies in the observable past depends on location in space-time. Two observers separated by a large distance may have access to different portions of cosmic history. They can later exchange records if their world lines enter one another's causal future. But at any local event, knowledge is limited by the signals that have had time to arrive. This makes the past not only earlier, but structured by access. Some past events lie inside the cone and can influence the present. Others lie outside it because their signals have not yet arrived or can never arrive under the geometry of the universe. Events outside both the past and future light cones are called space-like separated. No signal traveling at or below light speed can connect them at that stage. Different observers may disagree about their temporal order, but no disagreement can create a causal contradiction because neither event can influence the other. The cone preserves the order that matters physically. Anything inside the past light cone is earlier in a causal sense. Anything inside the future light cone can be affected later. The boundary itself traces the paths available to light. This causal architecture is more fundamental than a universal present. It does not require all observers to agree about distant simultaneity. It requires them to agree about which events can be connected by signals and which cannot. In that sense, the past light cone provides a more precise meaning of the accessible past than ordinary language does. It is not the entire past of the universe. It is the portion of earlier space-time capable of leaving an influence here. Even within that region, access is incomplete. Signals weaken, scatter, absorb, and mix. A detector records only what reaches it, and most details never do. Light from a distant planet may reveal a faint atmospheric spectrum while leaving its surface history almost entirely unknown. Gravitational waves may carry evidence of colliding black holes while preserving little about the matter that formed them. The cone defines what could influence the present, not what can be perfectly reconstructed. The past is causally available in fragments. This is why old light cannot settle whether the past still exists. The signal proves that an earlier event occurred and that its effects continue along permitted paths. It does not show whether the emitting event remains part of reality in the block universe sense, nor does it show that the event has been erased. Both interpretations can accept the same observation. A presentist can say that the event no longer exists while its light persists as a present physical object. An eternalist can say that the emission and reception are distinct locations within one space-time, both equally part of the total structure. The detector reading does not choose between them. It establishes a relation. The past event lies along the causal ancestry of the present one. General relativity makes the shape of light cones dynamic. Matter and energy curve spacetime, bending the paths of light and altering which events can communicate near a black hole. The cones tilt inward so strongly that beyond the event horizon, every future-directed path leads deeper inside. The horizon is not a wall, but a boundary in causal structure. Signals from within, it cannot reach distant observers. This shows that inaccessibility is not the same as non-existence. A region may belong to spacetime while being permanently unable to send information outward. The comparison does not prove that past events persist, but it weakens the instinct that whatever cannot be reached must therefore be unreal. Causal separation can arise from geometry itself. Cosmology introduces another limit. Because the universe expands and has a finite observable age, there are regions whose light has not yet reached Earth. There may also be regions from which signals emitted now will never arrive if cosmic expansion continues in the appropriate way. The observable universe is therefore not identical to the whole universe. It is the region connected to the present by past-directed light paths. Every observation is bounded by this horizon of causality. Beyond it, reality may continue, but no current measurement can confirm its detailed state. Once again, physics distinguishes what exists from what is accessible without automatically making them the same category. The past light cone applies that distinction within time. It gathers the events capable of leaving traces here, but it does not turn those traces into roads. Anciens photons, fossils, memories, and gravitational disturbances are arrivals from causal history. They are evidence that the present is not isolated. Every current event stands at the tip of an immense cone filled with earlier influences, converging from nearby moments and deep cosmic epochs. Yet all of those influences reach the present only by moving forward along their own world lines. The geometry permits inheritance, not reversal. Looking outward therefore becomes a form of looking backward, but never a form of stepping back. The past can remain visible long after it has become unreachable, and that difference prepares the harder question of why all records, cause, and physical transformations seem to point in the same temporal direction. The arrow of time appears most clearly where ordinary events refuse to run backward. A glass falls, strikes a floor, and breaks into scattered fragments. Heat leaves a warm object and spreads into cooler surroundings. Smoke disperses through a room. A living body grows older, while its earlier state survives only through records and memory. Each process has a direction that seems obvious before any equation is written. The reverse sequence can be imagined, but it is not encountered. Fragments do not leap together to rebuild the glass. Diffuse heat does not spontaneously gather itself into one warmer object. Smoke does not retreat into a compact shape and return to its source. This one-way character gives time its familiar orientation, separating what is called the past from what is called the future. Yet the fundamental laws governing many microscopic processes do not contain such an obvious preference. If the motions of ideal particles are reversed with perfect accuracy, the equations of classical mechanics often permit a valid reversed history. In electromagnetism, many interactions can also be described in either temporal direction when velocities and fields are transformed appropriately. Quantum mechanics adds subtleties, and some processes involving the weak nuclear interaction do violate time reversal symmetry, so nature is not perfectly indifferent to temporal direction at every level. Even so, the dramatic asymmetry of daily life is far greater than these rare microscopic violations can explain. The mystery is why a world built largely from reversible local laws produces irreversible large-scale history. The answer begins with probability, rather than with a force pushing time forward. A broken glass contains an enormous number of molecules. In principle, the equations governing those molecules allow trajectories in which every fragment, vibration, and pulse of air reverses and converges toward the original shape. But such a reversal would require correlations of almost impossible precision. Each molecule would need the correct position and motion. Each sound wave would need to return from the environment, and every exchange of heat would need to reverse in coordinated form. The reversed history is not forbidden in the same simple way that motion faster than light is forbidden. It is buried beneath an overwhelming imbalance in the number of possible states. There are vastly more ways for the glass to be broken, the heat to be dispersed, and the sound to be scattered than there are ways for all of those details to assemble into one intact arrangement. This imbalance is expressed through entropy. Entropy is often described as disorder, but that word can mislead. A more precise idea is that entropy measures how many microscopic arrangements are compatible with the same large-scale condition. A glass resting intact on a table corresponds to a comparatively narrow range of molecular configurations. A shattered glass spread across the floor can be realized in far more ways. A warm region beside a cool region is more constrained than a uniform temperature produced after heat has spread. When a system moves from a state with fewer compatible microscopic arrangements to one with many more, its entropy increases. The second law of thermodynamics states that entropy in an isolated system is overwhelmingly likely not to decrease. This law is statistical. It does not mean that a local decrease is impossible. Local decreases occur, and living organisms build structure while increasing entropy around them. For large systems, however, movement toward higher entropy is so much more probable that the reverse becomes effectively absent from experience. This statistical tendency creates the thermodynamic arrow of time. The future is the direction in which entropy increases. The past is the direction in which the same system occupied a more constrained state. That definition gives physical meaning to the asymmetry of records. A record is not information floating free of matter. It is a physical structure produced through an irreversible process. A footprint forms because pressure changes soil. A photograph forms because light alters a detector or chemical surface. A memory forms through changes in neural connections and activity. Each record requires energy, dissipation, and a larger environmental process in which entropy rises. Records therefore point toward lower entropy conditions from which they were produced. They do not normally point toward later events because record formation belongs to the same temporal orientation as heat flow and causal influence. This helps explain why conscious experience remembers one direction. The brain is not outside thermodynamics. It stores traces by changing its present state in response to earlier interactions. Those changes consume energy and release heat. Memory looks backward because record formation is part of the universe's entropy gradient. In a block universe interpretation, later events may still be part of spacetime, but the local structure of an observer contains records only of the lower entropy direction. The full geometry could be temporally extended while every conscious state remains oriented by the thermodynamic arrow. The experience of passage may therefore depend less on a moving present than on the unequal distribution of records across time. At each moment, a brain contains evidence of earlier states and uncertainty about later ones. Yet entropy does not explain itself. If high entropy states are overwhelmingly more numerous, a deeper question appears immediately. Why was the universe ever in a low entropy condition from which entropy could rise? The second law describes a tendency given a special starting point. It does not explain that starting point. A universe already near maximum entropy would contain little free energy, few stable gradients, and almost no capacity for complex structures to form. Stars shine because matter is not in complete equilibrium. Weather exists because temperature differences drive motion. Life depends on energy flowing from concentrated sources into cooler surroundings. Every organized process uses the fact that the universe has not yet exhausted its available gradients. The arrow of time therefore reaches back toward cosmology. The early universe was hot, dense, and remarkably smooth. Heat alone does not determine gravitational entropy in a simple way. A smooth distribution of matter can represent low gravitational entropy because gravity tends to amplify clumping. Over cosmic time, matter gathers into stars, galaxies, clusters, and black holes. These structures appear more organized to the eye, but gravitationally, they belong to a progression toward states with greater entropy. Black holes, in particular, carry enormous entropy associated with their horizons. The universe begins in a condition that allows gravity to produce structure while total entropy rises. Why that initial condition was so special remains one of the deepest questions in fundamental physics. Without it, the arrow would have no long slope to follow. Some proposals treat the low entropy beginning as a boundary condition of the cosmos. Others seek a dynamical explanation through cosmology, quantum gravity, or models with more than one temporal direction emerging from a central low entropy state. None has become a settled account. The uncertainty matters because the arrow of time is often mistaken for a basic rule written into every law. Instead, much of its strength may come from the universe's unusual beginning. Local processes point forward because they unfold within a larger history that started far from equilibrium. The glass breaks in one direction because the surrounding world already contains an entropy gradient. Sound disperses because the room, air, floor, and wider environment offer many degrees of freedom into which energy can spread. Reversing the event would require coordinating the entire causal environment that absorbed its traces. Irreversibility grows as information about the original state becomes distributed among more systems. At the microscopic level, that information may not be destroyed. It can become encoded in correlations too diffuse to reconstruct. In quantum physics, interactions can entangle systems, spreading information across joint states. To reverse the process would require control over those correlations with extraordinary precision. What appears as loss may therefore be practical inaccessibility rather than literal erasure. This resembles the larger question about the past. A previous state may leave information throughout the present without remaining recoverable as a complete event. Entropy explains why reconstruction becomes harder in one temporal direction, but it does not decide whether the earlier event still exists in spacetime. A presentist can say that entropy carries records of a vanished past. An eternalist can say that entropy orders different regions of a persisting block and gives observers within it an asymmetric perspective. Both accept the same broken glass and the same heat flow. The disagreement concerns what that order means. The arrow of time, therefore, adds an essential constraint without resolving the ontology. It explains why the past feels fixed, why the future feels open, why causes leave effects, and why memory accumulates in only one direction. It also shows why returning to an earlier state is not a simple matter of reversing a clock. A clock can be turned back as an object, but the environment that recorded its earlier motion has already changed. Air has moved, heat has spread, photons have escaped, and countless molecular correlations have formed. To restore the entire event would require reversing not one mechanism, but the expanding web of consequences connected to it. The past becomes inaccessible because every event releases traces into a universe whose number of possible configurations grows overwhelmingly toward the future. The forward direction of time is therefore less like a current carrying objects and more like a statistical slope embedded in physical history. Matter moves along world lines. Causes propagate within light cones, and entropy rises across macroscopic processes. Together, they create the stable orientation of experience. Yet the slope points back toward a still deeper absence, the unexplained low entropy condition from which the whole temporal distinction gains its force. Entropy does more than distinguish one direction of time from the other. It gives the universe a way to preserve traces. A footprint, a photograph, a fossil, a cooled ember, and a memory all exist because matter has been pushed from one arrangement into another, leaving behind a physical difference that can survive after the event itself is over. These differences are records. They are never abstract. A record is always a present configuration of particles, fields, or structures that carries information about an earlier interaction. The shape of a crater records an impact because rock was fractured, melted, displaced, and then allowed to settle into a stable form. A detector records a particle because the particle altered the detector in a way that can later be read. In every case, the record is produced through an irreversible process in which energy spreads and entropy rises. This is why entropy does not merely accompany the past. It helps define what the past means physically. A lower entropy state is one in which the possible microscopic arrangements compatible with the visible condition are comparatively restricted. A higher entropy state allows many more microscopic arrangements. When a system evolves naturally from the first kind of state toward the second, details of the earlier condition become dispersed into a wider environment. Some of those details are captured in stable structures. Most are not. The surviving structures become evidence. The rest becomes hidden in correlations too fine and too distributed to recover. A burned page leaves ash, heat, smoke, and altered air. Those consequences contain information about the burning, but they do not preserve the page in a form that can be read backward into existence. The process has not necessarily destroyed every microscopic detail in the deepest physical sense. Yet it has scattered those details across such a large number of degrees of freedom that reconstruction becomes effectively impossible. Entropy therefore creates a distinction between information being present somewhere in the total physical state and information being available as a usable record. The past remains influential because later states are constrained by earlier ones, but the route from effect back to full cause becomes narrower with every interaction. This gives records their asymmetry. A memory formed after an event can contain information about that event. The event does not normally contain a memory of the later recollection. A photograph develops after light strikes a sensitive surface. The photograph scene does not carry a completed image of the future photograph. Records point backward because their creation depends on entropy increasing from a more constrained state toward a less constrained one. Their direction is inherited from the thermodynamic history of the universe. The brain follows the same rule. Memory is sometimes described as though the mind reaches backward and retrieves a piece of the past, but the physical process is local and present. Neural systems change during experience. Connections strengthen or weaken. Molecular structures are altered. Later patterns of activity are shaped by those changes. Remembering is the activation of a current physical state that was formed through earlier interactions. The past event is not replayed in full. It is reconstructed from traces stored in the present brain, traces that are selective, incomplete, and vulnerable to change. This does not make memory unreal. It shows that memory is a thermodynamic record, one produced by energy consumption, molecular reorganization, and heat released into the surroundings. The ability to remember depends on a world far from equilibrium. A brain near complete thermal equilibrium could not maintain the organized gradients required for perception, storage, and recall. Life itself depends on low entropy resources. Organisms take in concentrated energy and matter, use them to maintain structure, and release more dispersed energy and waste. Local order is sustained by a larger increase in entropy. Memory belongs to this flow. The existence of memory therefore points beyond biology toward cosmology. Every record ultimately depends on the fact that the universe began in a condition from which entropy could rise. This idea is often expressed through the past hypothesis, the proposal that the early universe occupied an extraordinarily low entropy state. The low entropy beginning is strongly motivated by the observed arrow of time, but its ultimate explanation remains unsettled. The early universe was hot and dense, yet it was also remarkably smooth on large scales. At first, this can seem like a high entropy condition because hot matter appears disordered. Gravity changes the accounting. When gravity is important, a smooth distribution of matter can correspond to low gravitational entropy. Matter has many more ways to clump, collapse, form stars, assemble galaxies, and eventually create black holes than it has to remain almost perfectly uniform. The early smoothness therefore represents a special constraint. It gives cosmic history room to unfold. As small irregularities grow under gravity, structure forms while the total entropy increases. Galaxy condense. Stars ignite. Heavy elements are produced. Planets assemble. Black holes appear, carrying enormous entropy associated with their horizons. The visible complexity of the later universe emerges along a path toward greater overall entropy, not away from it. Greater structure does not always mean lower total entropy. A star is highly organized, but its formation and radiation increase entropy in the wider system. A living cell is intricate, but its metabolism disperses energy. Local records multiply because the universe has gradients available to consume. Every archive is paid for by dissipation. The past becomes richly documented precisely because entropy is rising. Yet the earliest low entropy boundary remains difficult to explain. If the laws of physics permit both temporal directions in many local processes, then simply running the equations does not select a universe with a low entropy past and a higher entropy future. A special boundary condition has to be imposed, derived, or explained by a deeper theory. Without that condition, a randomly chosen high entropy state would be far more probable than the orderly cosmic beginning inferred from observation. This leads to a profound tension. The second law appears universal in ordinary experience, but its power may come not from a microscopic command aimed toward the future, but from an exceptional condition near the beginning of cosmic history. The arrow of time could therefore be less like a law written into every interaction and more like a vast consequence of where the universe started. Some approaches seek to explain this through cosmological dynamics. Others appeal to quantum conditions, gravitational degrees of freedom, or models in which entropy rises away from a special central state in more than one temporal direction. There is no agreed solution. What remains clear is that the low entropy past is not a minor detail. It is the source of the gradients that make stars, chemistry, life, memory, and records possible. It is also what allows the distinction between past and future to be physically stable. In quantum theory, the formation of records is often connected with decoherence, the process by which interactions with the environment suppress observable interference between different possibilities. A microscopic system becomes entangled with surrounding particles, radiation, instruments, and observers. Information about the system spreads outward into many degrees of freedom. Once that information is embedded in the environment, certain outcomes behave as stable facts for practical purposes. Decoherence helps explain why macroscopic histories appear definite and why records persist. It also has a temporal orientation, because the environment begins in a condition with relatively little relevant correlation and then accumulates entanglement. Reversing that process would require extraordinary control of the environment, just as rebuilding a shattered glass would require controlling every fragment, vibration, and escaping photon. This connection does not solve the measurement problem in quantum mechanics, and it does not prove that the past survives as a region of a block universe. It shows something more limited but essential. The stability of facts depends on irreversible record formation. An event becomes part of history when its effects spread into enough systems that later states carry durable evidence of it. The past is not preserved as a complete duplicate. It is preserved through a hierarchy of records, each partial and physical. Some are fragile, like a thought that fades within seconds. Some endure for millions of years, like isotope ratios in rock. Some cross cosmic distances as light. Others vanish almost completely when their traces are absorbed into noise. Entropy makes forgetting common because it disperses detail, but it also makes remembering possible by allowing stable records to form. The same irreversible processes that hide most of the past also create the traces through which any past can be known. The present is therefore neither a perfect archive nor a clean break. It is a layered physical state containing compressed evidence of what came before, produced by a universe moving away from an unusually ordered beginning. Whether the earlier events themselves still exist remains unanswered. Entropy cannot decide between presentism and eternalism. It can explain why observers remember one direction, why records accumulate behind them, and why reversal becomes overwhelmingly inaccessible. It can show how the past remains written into matter without showing that the past remains open as a place. The deepest implication lies in the dependence of all temporal evidence on one ancient condition. Every photograph, fossil, scar, memory, and beam of old light ultimately inherits its direction from the low entropy state of the early cosmos. The records of the past are therefore not isolated remnants. They are local expressions of a universal asymmetry whose origin is still unknown. A photograph survives by becoming something different from the moment it records. Light from a scene changes a chemical surface or a digital sensor, and that altered material remains after the scene itself has changed. A fossil survives through an even longer transformation. Bone is buried. Minerals enter its structure. Surrounding sediment hardens, and a fragment of anatomy becomes part of rock. Memory follows another path, reshaping living neural tissue through patterns of activity and connection. These things are called records because their present form depends on earlier events. They allow the past to be inferred. Yet none of them contains the event in full. A photograph does not preserve every molecule of air around the camera, every sound beyond the frame, or every thought within the people shown. A fossil does not retain the living metabolism, behavior, and environment of the organism. A memory does not reproduce an earlier brain state exactly. It reconstructs from a limited physical trace. This gap between event and record is essential because records can prove that something happened without proving that the event continues to exist as a region of reality. The evidence is real. The conclusion that the past remains fully present does not follow automatically from it. Every record exists now. Its matter, energy, and organization belong to the present world. Even ancient light arriving from a distant galaxy is a present electromagnetic field at the detector, though its structure was shaped by an emission event long ago. The record carries a relation across time. It is not the earlier event transported forward without change. A camera image of a lightning strike may endure after the storm has dissipated, but the electrical discharge, heated air, and surrounding motion do not remain inside the image. The record preserves selected correlations. It tells later systems that certain conditions once existed because its current arrangement would be unlikely without them. Scientific reconstruction depends on this logic. Tree rings reveal seasons of growth. Ice cores preserve layers of trapped gas and chemical traces. Radioactive isotopes constrain the ages of rocks. Light spectra reveal the composition and motion of stars. None of these observations reopens the original environment. Each establishes a chain of inference from a present state to an earlier cause. The strength of the inference depends on how well the physical process linking cause and record is understood. A crater suggests an impact because mechanics, geology, heat, and shock waves explain how such a structure forms. A spectral line suggests a particular element because atomic physics explains how that element interacts with light. The past is knowable through present evidence because physical law connects states across time. Yet knowledge of a cause is not possession of the cause itself. The distinction becomes clearer when records decay. Memories change through recall, suggestion, emotion, and later experience. Photographs can be altered. Fossils are incomplete. Geological layers can be folded, heated, or eroded. Light can be absorbed, scattered, and redshifted before reaching a telescope. A record is not a transparent window. It is a surviving object with its own history. To interpret it, science must reconstruct not only the event of interest, but also the transformations that occurred afterward. This is why the past is never simply found waiting inside the present. It has to be inferred through layers of physical change. Some records preserve more detail than others. But no known record preserves everything. The information lost from practical access does not always vanish from the deepest equations. Microscopic details may spread into correlations among particles, radiation, and the wider environment. In principle, a complete description of all those correlations might contain enough information to distinguish one earlier state from another. In practice, the required control is beyond reach. A spoken word changes the air, walls, bodies, and surrounding electromagnetic fields in many ways. Those changes continue to interact and disperse. Reconstructing the original word from the total later state would require knowledge and control of an immense environment. The information may not be cleanly destroyed, but it becomes inaccessible as a usable record. This is one place where the phrase, "the past survives," can become ambiguous. The past may survive causally because later states depend on it. It may survive informationally because traces remain distributed through the present. It may survive geometrically if earlier events are still regions of spacetime within a block universe. These are different claims. Causal survival does not prove geometric survival. Informational traces do not establish that an event remains available as a location. The present can contain consequences of something that no longer exists under a presentist interpretation. The same evidence can be described by an eternalist as interactions between different regions of a single spacetime. Records alone do not decide between these pictures. They are compatible with both. Memory provides the most intimate example because it creates the feeling that the past remains internally present. A childhood room can appear again in thought with color, shape, and emotional weight. Yet the recalled room is not the original room restored. It is a new event in the present brain, produced by a network of traces that has changed since the earlier experience. The remembered image may combine accurate detail with later interpretation. Memory is therefore evidence of continuity between earlier and later states, not evidence that awareness has reached backward into the earlier moment. The brain does not leave the present. It generates a present reconstruction shaped by the past. The same principle applies to collective memory. Archives, monuments, recordings, ruins, and written histories extend the capacity of societies to preserve information, but they remain material objects that must be maintained and interpreted. A text survives because ink, paper, digital storage, and copying processes continue. A civilization can lose knowledge when records decay or become unreadable. The past does not remain equally available simply because it happened. Its accessibility depends on which traces endured and whether later observers can understand them. This introduces selection into history. Events that leave durable physical marks become easier to reconstruct. Quiet events with few surviving consequences may disappear almost completely from knowledge. The universe does not preserve every moment with equal clarity. It produces an uneven archive shaped by energy, material stability, en chance, and the interests of record-making organisms. Light itself is often imagined as a perfect messenger from the past. But even light is selective. A telescope receives only the photons that enter its aperture. Dust may block some wavelengths. Cosmic expansion may stretch others. Detectors add noise and impose limits of resolution. What arrives is enough to reveal structure, but never the whole event. Looking at a distant galaxy means receiving one narrow portion of its earlier radiation field, not observing every process occurring there. The past light cone is filled with signals, but access remains fragmentary. This matters for the title question because visibility can be mistaken for continued existence. A star seen in old light may already have changed, yet the arriving image remains physically real. The image proves that the earlier stellar state influenced the present. It does not show whether that state still exists in a four-dimensional ontology, nor does the inability to revisit the star prove that the state has been erased. The record leaves the metaphysical question open. Fossils make the same point on Earth. A trilobite fossil can reveal anatomy, growth, injury, and environment. But the organism is not sleeping within the stone. Its biological processes ended. The fossil is a later mineral structure related to the organism by burial and transformation. Under presentism, that relation connects a current object to an event that no longer exists. Under eternalism, both organism and fossil occupy different regions of one space-time history. The observed fossil is identical in both interpretations. What changes is the account of temporal existence surrounding it. Records, therefore, provide strong evidence about what occurred and weak evidence about what it means for an event to remain real. They establish continuity, causation, and physical inheritance. They do not establish resurrection, accessibility, or equal existence across time. This restraint does not diminish their importance. Nearly all knowledge of events beyond immediate experience depends on records. Cosmology reconstructs the early universe from radiation. Element abundances, large-scale structure, and gravitational signals. Paleontology reconstructs vanished ecosystems from bones. Impression, isotopes, and sediment. Personal identity relies on memory, bodily continuity, and social records. The present is intelligible because it is filled with traces of earlier states. Without records, the world would still have a causal past, but observers within it would possess almost no history. The existence of records gives the past a practical reality. It shapes decisions, identity, prediction, and explanation. Yet practical reality is not the same as ontological persistence. The record is here. The event was there in time. Whether there remains a meaningful sense in which the event still is depends on the deeper interpretation of space-time. Memory, fossils, photographs, and ancient light can carry the question to that boundary. But they cannot cross it. They show that the past is not nothing, because the present is structured by what came before. They also show that survival is always partial when it takes the form of a trace. What remains is information embodied in new matter and new events. Not the complete return of the old. The past can be preserved without being restored, influential without being reachable, and perhaps real without being available. That separation becomes decisive when the inquiry turns from records to return, because even a universe that never erases its past may still forbid every path leading back into it. A closed time-like curve is a path through space-time that returns to its own past while always remaining locally future-directed. The phrase sounds contradictory only because ordinary experience separates moving forward in time from arriving at an earlier event. In general relativity, however, motion is determined by space-time geometry, and some exact solutions to Einstein's equations contain trajectories that loop back toward their own starting region. An object following such a path would never locally reverse its clock. Its proper time would continue increasing along the journey. Yet the geometry would bend the route so completely that the traveler could encounter an event lying in the traveler's own causal past. This is the mathematical core of time travel to the past in relativity. It does not begin with a machine moving faster than light, and it does not require time to flow backward along the traveler's body. It begins with a space-time whose global structure allows a future-directed worldline to close. The best-known early example comes from a rotating cosmological model developed by Kurt Gödel. In that solution, the universe as a whole rotates in a way that tilts light cones across large distances. A path that begins locally within the future light cone can continue through the curved geometry and eventually return to an earlier event. The equations permit the loop because the causal structure is distorted on a cosmic scale. Gödel's universe is mathematically consistent as a solution of general relativity, but it does not resemble the observed universe in several important respects. Its large-scale rotation, matter distribution, and global behavior do not match modern cosmological evidence. The solution, therefore, demonstrates possibility within the equations, not actuality in nature. It shows that general relativity alone does not automatically forbid every form of causal looping. It does not show that the real cosmos contains such loops. Other models produce similar possibilities under different conditions. A rapidly rotating cylinder of idealized matter can drag spacetime strongly enough to permit closed time-like curves in certain calculations. But the required cylinder is often infinitely long or depends on unrealistic material properties. Some rotating black hole solutions contain regions where the causal structure becomes strange enough for loops to appear. Yet those regions lie beyond horizons and near internal instabilities that may destroy the idealized geometry. Wormholes, if they existed and could remain open, might also connect separated regions of spacetime. If the two mouths of a wormhole experience different amounts of proper time because of motion or gravity, passing through one mouth and emerging from the other could, in principle, create a route into the past relative to the surrounding universe. The idea follows known relativistic time dilation. But the wormhole itself remains speculative. No traversable wormhole has been observed. And the matter required to stabilize, one may need negative energy conditions that cannot be sustained in the necessary form. Each proposal reveals the same pattern. The equations admit unusual geometries. But the physical requirements become increasingly severe as the route approaches a usable time machine. Mathematical consistency is only the first test. A spacetime model must also arise from plausible matter, remain stable under disturbance, survive quantum effects, and fit the observed universe. Many time travel solutions fail one or more of these tests. Some require infinite structures. Some depend on densities or rotations that no known material can support. Some hide the relevant region behind an event horizon. Some appear unstable when even small amounts of radiation or matter are included. The existence of a solution on paper therefore cannot be treated as evidence that nature permits construction or travel. General relativity describes an enormous family of possible spacetimes, including many that are not realized. A map of mathematical possibility is larger than the territory of the universe. Closed time-like curves also create causal paradoxes, though paradox alone does not prove impossibility. The most familiar problem involves an action that prevents the conditions required for the action itself. If a traveler returns to an earlier event and changes the chain of causes leading to the journey, then the world line appears inconsistent. Relativity does not supply a simple rule for resolving this. One response is the principle of self-consistency, according to which only histories that fit together without contradiction can occur. Under such a rule, a traveler could enter the past, but every action taken there would already be part of the history that led to the journey. Attempts to create contradiction would fail through ordinary physical causes, not because an external force rewrites events. The path would close consistently. This picture fits naturally with a block universe because the entire loop exists as one fixed spacetime structure. The traveler's arrival in the past was always part of that past. Nothing is changed from one version of history into another because there is only one complete history. Yet this solution changes the meaning of freedom and intervention. The past can be visited, but not altered into a state inconsistent with the journey. A second response uses branching histories. Entering the past might lead into another branch rather than rewriting the traveler's original history. In that case, the journey would not form a closed time-like curve within one classical spacetime in the simplest sense. It would depend on a particular interpretation of quantum theory and a structure beyond ordinary general relativity. Such branching proposals are logically suggestive but remain speculative. They do not provide observational evidence for time travel. Quantum theory may also place limits on closed time-like curves before paradox becomes relevant, near a region where causal loops are about to form. Quantum fields could produce large amounts of energy. That energy might curve spacetime strongly enough to prevent the loop from developing. This possibility is associated with the idea of chronology protection. The proposal that physical law prevents macroscopic violations of causal order. No complete theory of quantum gravity exists to establish the principle generally. Calculations in restricted settings offer hints, but they do not amount to a universal proof. The boundary between allowed geometry and forbidden chronology may therefore depend on physics not yet fully understood. This uncertainty should not be mistaken for evidence that time machines are likely. It means only that the final prohibition, if one exists, has not been derived in every possible case. Observationally, no closed time-like curve has been detected. No signal has been confirmed as arriving from its own future. No wormhole has been found. No region of space-time has been shown to allow a material object to return to an event in its own past. High-precision tests of relativity confirm time dilation, gravitational redshift, light bending, orbital precession, and gravitational waves. But none confirms backwards time travel. The theory succeeds spectacularly in regimes where causality remains ordinary. Its exotic solutions occupy a far less secure domain. The difference between these domains is crucial. Relativistic travel into the future is not speculative in the same way. A clock moving rapidly or remaining near strong gravity can accumulate less proper time than another clock. When the clocks reunite, the traveler has experienced less elapsed time. This is sometimes described as traveling into the future because more time has passed elsewhere. The effect is real and measured. It does not allow return to an earlier event. It only changes how much proper time different world lines contain. Travel to the past requires a much stronger distortion of causal structure. It asks spacetime to provide a route that circles back rather than merely aging observers at different rates. The presence of closed time-like curves in mathematics also does not prove that the past remains present in the block universe sense. A presentist could reject such spacetimes as unphysical or treat them as signs that general relativity has reached a limit. An eternalist could regard the loop as one more fixed structure within the block. The metaphysical interpretation does not create the curve. The geometry must first allow it. Conversely, a block universe can contain a complete past without permitting any return to it. Most ordinary relativistic spacetimes have well-behaved causal order and no closed time-like curves. The past may remain part of the manifold while every future-directed path leads away from it. Persistence and accessibility remain separate. That separation removes a common misunderstanding. If the past still exists, then perhaps it should be reachable. Relativity gives no such guarantee. A region can exist within a geometry while lying outside every permitted route from the present. Event horizons already show that causal accessibility can be restricted without erasing the hidden region. Temporal order may impose an even stronger barrier. The universe could preserve every earlier event as part of its four-dimensional structure and still prevent all world lines from turning back. Closed time-like curves are important not because they offer a practical design, but because they reveal how much the equations depend on global geometry. They show that local obedience to the speed of light does not always guarantee a simple global order of cause and effect. They also expose the limits of treating mathematical possibility as physical prediction. General relativity leaves narrow doors open in highly unusual spacetimes, while observation has not shown that nature walks through any of them. The past may be part of reality, but no known evidence turns that possibility into a destination. The Wheeler-DeWitt equation presents one of the strangest clues in modern physics because the familiar symbol for time does not appear in it in the ordinary way. The equation arises in attempts to combine quantum mechanics with general relativity, treating the geometry of space itself as a quantum system. In ordinary quantum theory, a state changes with time, a wave function evolves, probabilities shift, and measurements are compared from one moment to another. General relativity, however, does not place matter inside a fixed temporal background. Spacetime is dynamical. Its geometry responds to matter and energy, and the rate measured by a clock depends on the path that clock follows. When these two frameworks are brought together, the external time used by standard quantum theory becomes difficult to identify. The result is often called the problem of time. At the most fundamental level described by some quantum gravity approaches, the universe can appear frozen, represented by a state that contains relationships, but no obvious universal parameter marking change. This does not mean that nothing happens. It means that the time measured by clocks may not be an ingredient placed beneath reality. It may emerge from the way parts of the universe change relative to one another. A clock is then not a device reading an independent cosmic flow. It is one physical system whose changing state is correlated with the changing state of another. The position of a pendulum, the oscillation of an atom, the expansion of the universe, or the decay of a particle can serve as a temporal reference because other processes vary in a stable relation to it. Time becomes relational. One subsystem plays the role of a clock, and another is described as evolving with respect to that clock, from inside the universe. This can produce the ordinary appearance of succession, even if the total quantum state is described without an external time. The distinction is subtle because every actual measurement already works through relations. A clock never captures time directly. It counts repeated physical changes and compares them with other changes. The emergent view asks whether this practical fact reaches all the way down to the foundations. Perhaps there is no time beyond the network of correlations. Perhaps what appears as a flowing background is a large-scale approximation. Much as temperature emerges from the collective motion of molecules, even though no single molecule possesses temperature by itself. The analogy is useful but incomplete. Temperature can be derived from a well-understood microscopic theory. Time in quantum gravity has no single accepted derivation, and the frameworks being explored remain unfinished. Some approaches recover an approximate time only under special conditions, such as when one part of the gravitational field behaves classically enough to serve as a background for other quantum systems. Others define time through entanglement, causal order, or changes in relational observables. The shared possibility is that familiar temporal flow may belong to the effective world of large objects and stable records rather than to the deepest description of nature. If so, the status of the past changes again. In a classical block universe, past events remain as earlier regions of a four-dimensional spacetime. In an emergent theory, even spacetime may not be fundamental. The past could not simply be pictured as a place still lying behind the present, because the entire geometry containing behind and ahead might itself arise from a deeper quantum structure. What survives at that level may be a pattern of correlations from which temporal order can be reconstructed. Earlier and later would then describe relationships within the emergent pattern, not positions inside an independently existing container. This possibility does not make the past less real, but it changes what reality would mean. A childhood event, the formation of Earth, and the emission of ancient light might remain encoded in the relational structure from which spacetime emerges. Yet, calling them still existent could be misleading if existence is being imagined as occupancy of a permanent temporal location. The deeper theory may preserve no such locations. It may preserve only the complete set of correlations that allows observers within the universe to describe an ordered history. The block universe and emergent time are therefore not simple rivals. A timeless fundamental state could give rise to an effective spacetime that looks block-like. The whole history might be encoded within one quantum structure, while observers inside it experience local change through correlations and entropy. Alternatively, spacetime and temporal order might emerge dynamically in a way that gives becoming a more basic role at the effective level. Current theory does not decide among these possibilities. The problem is sharpened by quantum mechanics, because quantum states are not ordinary lists of definite events. They can contain superpositions, entanglement, and probabilities that resist a single classical history. Decoherence helps explain how stable records and apparently definite sequences emerge when systems interact with their environments. It selects robust patterns that behave classically for practical purposes. Yet, decoherence does not by itself explain why one outcome is experienced, nor does it establish whether all possible histories exist, whether one history becomes actual, or whether the distinction is framed incorrectly. The nature of time is therefore entangled with the interpretation of quantum theory as well as with the geometry of relativity. A complete account would need to explain why clocks work, why causality remains stable, why entropy points in one direction, why memories refer to lower entropy states, and why spacetime appears smooth on large scales. It would also need to recover the successful predictions of general relativity and quantum physics in the domains where both are already tested. No current theory has achieved all of this with decisive experimental confirmation. Loop quantum gravity, string theory, causal set approaches, and other programs offer different pictures of the underlying structure. Some preserve a fundamental form of ordering. Some replace continuous spacetime with discrete relations. Some treat geometry as emerging from quantum entanglement or other non-spatial ingredients. Their mathematical development is substantial, but direct evidence remains limited. The absence of a final theory places a boundary around every confident claim about the survival of the past. Relativity removes a universal present and makes the block universe plausible. Thermodynamics explains why records point toward lower entropy conditions and why reversal becomes inaccessible. Quantum theory suggests that definite histories may emerge from a deeper structure. None of these results alone proves that earlier events continue to exist exactly as present ones do. The title question can therefore be answered only conditionally. If spacetime is a complete four-dimensional reality, then the past may never disappear. It remains as part of the total geometry, though no ordinary world line can return to it. If only present events exist, then the past survives through causal influence, information, and material records, but not as an existing region. If reality grows, the past may remain while the future is added. If time itself emerges, then the distinction between survival and disappearance may be a feature of the effective world rather than a fundamental question. Each view preserves part of experience and sacrifices another. Presentism protects the immediacy of becoming, but struggles with relativistic simultaneity. Eternalism fits spacetime geometry cleanly, but treats passage as non-fundamental. The growing block preserves both an existing past and an open future, but needs an account of how the boundary of reality is defined. Emergent time may dissolve the conflict at a deeper level, but only by replacing familiar temporal language with a theory not yet complete. The mystery endures because physics has separated several ideas that daily life joins together. Existence is not the same as accessibility. A record is not the same as an event. Temporal order is not the same as temporal flow. A mathematical representation is not automatically an ontology. The present is locally real without being universally shared. The past can be causally necessary even if it is no longer present. And it can be geometrically included even if it can never be reached. These distinctions do not weaken the question. They reveal why it has resisted a simple answer. The past may not disappear in the way a sound fades or a light is extinguished. It may remain woven into spacetime, encoded in correlations, or preserved only through the present structures it helped create. The final uncertainty is not whether the past matters. Every current state proves that it does. The uncertainty is whether reality contains earlier events themselves, or only a universe that bears their consequences, until a deeper theory of time unites gravity, quantum mechanics, entropy, and experience. The past remains suspended between geometry and memory, perhaps permanent, perhaps absent, and still beyond the reach of any clock. Time remains difficult because it is both intimate and unreachable. Every life unfolds through it. Every star is shaped by it. And every physical record carries the direction of its passage. Yet the deeper structure behind that experience is still uncertain. Relativity removes the comfort of a universal present and replaces it with local clocks, world lines, light cones, and a spacetime whose events may belong to one larger geometry. Thermodynamics explains why memories gather on one side of experience, why traces accumulate, and why earlier states become harder to recover as information spreads through the world. Quantum theory then opens a quieter possibility. That time itself may emerge from relations more fundamental than space, clocks, or change as they are ordinarily understood. None of these ideas restores the past as a place that can be entered. No known path leads back to a vanished room, an ancient ocean, or the first light of a distant star. Yet none of them allows the past to become meaningless. It remains in causes, in structure, in memory, in the elements formed before Earth existed, and perhaps in the geometry of the universe itself. The question of whether it still exists may depend on what existence means when time is no longer treated as a river carrying reality away. Perhaps every event remains where it occurs within spacetime. Perhaps only its consequences continue. Perhaps both descriptions are shadows of a deeper account in which past and present emerge together from a timeless order. For now, the mystery stays open, not empty, but held between evidence and interpretation. The clocks continue, the records deepen, and the universe carries its history forward in forms that never fully reveal whether anything has truly been left behind.